Okay, welcome back. Now we're going to go over core thermal limits. Right? Topic 193009. So core thermal limits. We've gone over in the past changing thermal conductivity and getting a different fuel centerline temperature. There's another one of these questions, or actually another two of these questions in the exam bank about changing power levels, which are closely related. So we'll go over those two questions. And remember, this is a 1 out of 50 shot. So you're going to get one question for core thermal limits on your GFES exam. And you have I guess a 2 out of 35 chance of this being the question. So you recall earlier, we did the different fuel centerline temperatures, but we assumed that the power levels and the coolant temperatures were going to stay constant, right? So that would leave us to believe that Q dot in state 1 is equal to the thermal power in state 2. Well, if you look in this case, given the following initial parameters for a segment of fuel rod, 3 kilowatt per foot power density, LPD, linear power density, coolant temperature of 579, and a fuel centerline temperature of 2400. And reactor power is increased such that the following parameters now exist. So now we've got a different centerline temperature, or I'm sorry, a different coolant temperature, and we will have a different centerline temperature. So power density of 5 kilowatts, 590 degree coolant temperature. We're looking for the fuel centerline temperature. Assuming no boiling occurs and coolant transfer or coolant flow rate is unchanged, what will be the new stable fuel centerline temperature? Okay, so in this case, we cannot say that Q1 equals Q2. But what we can do is set up a ratio. Q dot 1 over Q dot 2 is proportional to 3 kilowatts per foot divided by 5 kilowatts per foot. And what that means is that this is going to equal UA delta T, right? U1A1 temperature centerline 1 minus temperature coolant 1 divided by U2A2 temperature centerline 2 temperature coolant 2. Alright. Now, we didn't hear anything about the thermal transfer coefficient changing, so those are going to equalize. The U's. The areas of the coolant channel are going to change, so that's going to go out. So, and let's change this, kilowatts per foot is going to change out. So my equation is going to be 3 divided by 5, excuse me. Temperature centerline 1 minus the temperature centerline 1 is going to be 2400 minus 579 divided by temperature centerline 2, which is what we're looking for, and that's going to be minus 590. Let me do a little algebra here. Temperature centerline 2 is going to be equal to 5/3. And then we're going to do this quantity of 2400 minus 579 Let me erase a little bit. And we're going to have to add 590 degrees. I think that will work out for us. Like I say, easy problem if you just do it that way. It's lining them up and figuring out the ratios. It's a hard part. 5 times the quantity, 2400, minus 579, divided by 3. It's going to be plus 590. That's going to be equal to 3625. Temperature center line 2 is going to be equal to 3625, and that's degrees Fahrenheit. The answer is C. 3625. Answer C. Alright, so that was pretty close, huh? I wonder what happened there. I bet you if you added 579 instead of this 590, that would be a good distractor. Let's try that. Okay. So one of the distractors, this one, right, which isn't right, that's going to be if you add 579 here. So if you juxtapose that number, we don't want to do that. So I'll be wary of that, okay? Now there's only really one more question on this topic. What page is it on? Gotta find it. It's going to be 3895 on page 26. Excuse me while I scratch my way up to 26. Alright, so here we are. Okay. This is question 3895. Same topic. And refer to the drawing of fuel rod and fuel coolant flow channel. We don't really have to. We've seen it before, right? Given the following initial stable core patterns, 50% power, 550 degrees temperature coolant, and 2250 at temperature center line. Assume total heat transfer coefficient and reactor coolant temperature do not change. Okay, cool. What will the stable fuel centerline temperature be if reactor power is increased to 75%? So again, we can't say that Q dot 1 is equal to Q dot 2, right? Because that's not right. But we can't say that Q dot 1 over Q dot 2 is going to be equal to U. What's happening? Sorry. U1A1 temperature centerline 1 minus temperature coolant 1 over U2A2 temperature centerline 2 minus temperature coolant 2. And we can't say U1 equals U2. A1 equals A2, and TC1 is equal to TC2. Alright, so now a bunch of stuff is going to clear off. And so U1, U2, A1, A2. We'll figure that out. So now we say that Q1 is 50% over 75% is equal to 2250 minus 550 divided by temperature center line 2 minus 550. Alright. So I'll do a little fancy algebra and I'll say temperature center line at point 2 is equal to 75 over 50 times 2250 minus 550. I'm running out of room. Ugh, sorry. That's going to be in degrees Fahrenheit. And then we're going to add 550. because we assumed reactor coolant temperature did not change. All right. So now we go to the calculator. 75 times quantity 2250 minus 550 over 50%, and that's going to be plus 550. I have 3100 degrees Fahrenheit. Temperature center line 2 is equal to 3100 degrees Fahrenheit. It's going to be D, 3100. All right. So, I would assume that one of these answers is, one of these distractors is testing to whether you know that that is not the case. So, if you read the proper question. Anyway, I hope it's pretty easy for you. Hope you enjoy it. So, that's all I have to say to you people on this subject.